Hey, welcome to Chapter 8. Congratulations on Chapter 7. My intent is to move very quickly through Chapter 8, the chapter on powers and roots. I'm going to spend a little bit more time on 8-1, but after that we'll be just kind of combining it, moving pretty fast. I find this is material that most students really already know, and so there's not a lot of reason to spend too much time on it. Better to move ahead. If my assumption is wrong, if you find you are having difficulty with this, please come and see me so we can work out how to get you some more practice with it and more instruction in these particular problems. But having said that, 8-1 is something a little different. I want to make sure you get it because it's a pretty powerful technique. Read through the chapter opener about powers and roots. Then we'll go ahead and get into 8-1, the multiplication counting principle. Now you're familiar with this. You used to call it factorials. Remember, like 5 factorial? I think you remember seeing that. That's 5 factorial is equal to 5 times 4 times 2 times 3. Man, getting late. Okay. 5 times 3 times 2 times 1. So let's say we have a race and there are 5 racers. What are the possible ways they could finish? Well, there are 5 different possibilities for the first place racer. Once first place is gone, well, there's only 4 racers left, so there's 4 possibilities for the second place racer. And then third place, so there's 3 left. And for, say, first place, second place, third place, fourth place, there are 2 left. And finally, the person who finishes last is last, and there's only 1 person. So this is a multiplication counting principle type of problem. And it has to do with, to know how many different permutations there are, we have to know how many choices there are for each category. We have 5 choices, then 4 choices, then 3, then 2, then 1. You can run the numbers and get your results, right? No? Okay, 120. 120. 120 different ways the race could be finished. Okay, let's take a look into the lesson. And here is example 1. In an apartment building, each apartment has a number from 1 to 9, followed by a letter from A to F. For example, one apartment designation is 9A. How many different apartment designations are possible in this building? Well, we need to break this down into 2 categories. The first one is the numbering. So for the numbers, we have how many choices? 1 to 9 is 9 choices. And then for the alphabet, we have how many choices? So A, B, C, D, E, F. That looks like 6. So there's 6 different ways we can orient the letters. Well, that's our first choice is 9. We have 9 choices for the first one, times 6 choices for the second, and 9 times 6 is 54. There are 54 different possible combinations for this apartment building. Okay, it's a matter of identifying choices. Example 2. A little different problem here. A combination lock requires a sequence of 3 numbers from 0 to 99 to open it. How many different possible codes are there? Well, there are 3 numbers needed. And so we have the first number, the second number, and the third number. And how many possibilities are there? Well, from 0 to 99 is how many? Well, 0 is counted. So that's 1. Which means 99 would be 100. So there are 100 possible ways to open it in the first case. there's 100 possible ways for the second number, and there's 100 possible ways to do the third one. So this gives us the possible codes, and it's 100 times 100 times 100 times 100. Well, we've seen this before. This is repeated multiplication, which leads us to powers. So it's 100 cubed. That's repeated multiplication, so it's 100 to the third power. And 100 to the third power gives us 1, so 1 followed by 6 zeros. 1, 2, 3, 4, 5, 6. That'd be 1 million is our solution. So there are a million different possible codes in the 0 to 99 sequence. Now let's look at a combination problem. This is interesting because it's the kind of thing we might see. Suppose a test has 10 true-false questions and 8 multiple-choice questions with 4 choices. What is the probability that a person could guess on each of the 18 questions and answer them all correctly? Now, if we assume, which we do, that it's equally likely every one is an independent event, then for the multiple-choice test, there's 10 questions, and each one is a true-false. So how many choices are there? Well, for question 1, there's 2 choices. For question 2, there's 2 choices. 3, 4, 5, 6, 7, 8, 9, and 10 all have 2 choices. So that's how many choices we have, and we count them up. Well, there's 10, right? There's 10, and that's going to be repeated multiplication. Repeated multiplication leads us to powers. However many times we repeat that multiplication is our power. So 2 to the 10th power equals the number of true or false choices. Well, then we have 8 multiple choice questions. So 1, 2, 3, 4, 5, 6, 7. There are 8 questions. How many choices are there? Well, for the first one, 4. Second one, 4. All of them are 4. Right? They all have 4 possible choices for multiple choice. Again, this is going to be repeated multiplication. So it's this choice times that choice times that choice. There's 8 different questions, so it's 4 to the 8th power. The answer to our question is how many to get correct. Well, first let's find out what it would take to get them all wrong, if you will, or how to get it all right. So there are choices here. I have 2 to the 10th. So I have 2 to the 10th power times 4 to the 8th power. And that's going to equal 1,024 times 65,536, which equals, when we put them together, 67,108,864 possible different ways to answer the questions on this test. Now, what we were asked is, what's the way to answer them all correctly? Well, out of the 67,108,864, there is only one way to answer them correctly. So our one way is one way to answer them correctly out of 67,108,864, and that equals, this is a very small number. It's our number of choices, how many different ways we can do it, divided into the number of outcomes we could have. There's one perfect outcome, and that's going to be approximately equal to 0.000 0.000 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7 zeros and a 1. I don't know what that is. That's the probability that answering the questions randomly, just without knowing, and getting it perfect, a perfect score on the test. We can write a large number like this. We can use scientific notation. In this case, it's how many decimal places do we have to move the decimal point to get it to the right of 1, and that's 1, 2, 3, 4, 5, 6, 7, 8. So 1 times 10 to the negative 8th is our answer for this particular problem. If I wanted to write this in the other number here in scientific notation, sorry, let me go back. If I wanted to write our answer here in scientific notation, that's going to be 6.7, and I could maybe stop right there, but 108,864 times 10 to the, and it's how many decimal places did I have to move to get it to here? It was here to begin with. That's where it begins, right? 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7. And that'll be 6.7108864 times 10 to the 7th power is how we write that in scientific notation. Remember scientific notation, the leading digit is in the ones place, followed by a decimal point, whatever other numbers we need, times 10 raised to some power. Could be negative, could be positive. That is scientific notation. Okay guys, that's 8-1. Good luck on the self-test, and then when we get going on 8-2, we will be doing a clump of these together, 8, 2, 3, and 4. See you in class.